We're going to continue on with our practice final exam, and we're going to get into question 3. So the first question was about corrosion, second question on polymers, and now we're back to exam 1 material. So that could include everything in up to bonding, basically structure, defects, planes, directions, family of planes, families of directions, et cetera, et cetera. It could also include defects. It could include diffusion. It could include phase diagrams. And let's kind of take a look at one of the example problems we have below. So we have 3 unit cells below, A, B, and C. We could already see that A is an FCC material. So you can see kind of, again, these atoms, each of these atoms at the face. So A is FCC. If we're FCC, we know we have 4 atoms. B is BCC. Excuse me, let's undo that. B is BCC. There are 2 atoms. And C is also FCC as well. So there are 4 atoms there as well. Excellent. So let's look and see what the question's asking. Getting a little ahead of ourselves as usual. So it says to label all the directions and planes in the unit cell using proper Miller indice notation. So what I'm going to do is change color. So I'm going to label this guy is 1. I'll label this one as 2. This one is 3. And this one is 4. So for my 1, if I'm doing directions, so looking at 1, I want to look at the arrow here minus here for a vector. So I know that point is going to be at the arrowhead, where the pointy part. That's a technical term. That is going to be at 1. The y-axis there is going to be 0, and then 1 at z. Minus the origin, which is just 0, 0, 0. So we are just left with the direction there. It's just going to be the 1, 0, 1 direction. We are using brackets. Again, we use parentheses for planes. So let's look at 2 now. So 2, we are starting, or our little arrow, we're going from here to here. You can kind of see that. So we are going, we're starting at, or our arrowhead is at 0, 0, 1, minus, we are ending at 1, 1, 1. So we are left with 0 minus 1 is our 1 hat, 0 minus 1 is our another 1 hat, and 1 minus 1 is 0. So that's for 2. Let's look at 3. So let's put it over here. So 3, I am ending at this location here, and that is basically 1 half, 1 half, 0, minus my starting point is going to be, again, 0, 1, 1. So 1 half minus 0 is going to be a half. 1 half minus 1 is going to be minus a half. And then 0 minus 1 is going to be 1 half. So we need to multiply this out in order to get to our basically proper notation here. So multiplying by 2, we are going to have 1 minus 1 hat, 2 hat. So that's our direction there. And then finally for 4, again, we're ending up at that 1 half, 0. And here we're starting at minus 0, 0, 1. So we subtract that, we get half, half, 0 minus 1, 1 half. So we get 1, 1, 2 bar. That's it. So those are our directions. Now, how do we deal with planes? So let's scroll up and look at the planes in A. So the plane in A, we need to look at what are our intercepts. So let me scroll up a little bit so we have some room. So what are our intercepts for A? So our H-intercept occurs here, 1, 1, 1 for all of us. So H, K, L indices are intercepts, 1, 1, 1. To get our plane, we take the reciprocal, so 1 over that, it's just 1, 1, 1. B, let's look at what we've got here, H, K, L. What are our intercepts? So we intersect the x-axis here at 1. Where do we intersect our k-axis? That's going to be at a half. What about our z-axis? Do we kind of ever cross through here? No. So it is infinite. So our plane is 1, 2, 0. That's it. And C, I like this one. C is a little tricky. So H, K, L. Where do we intersect H? 1 right here. Do we ever intersect Y? No, we'll never intersect there. What about Z? So we're already at 1 here. We're not crossing. But if this plane continues, you could kind of prove geometrically that we're going to cross that at 2. So now our plane is reciprocal 1, 0, 1/2. That's not right. We need to multiply out 0, 1. That's it. Again, choosing here as our origin. That's it for the directions and planes. So that's all we need to work with in here. So we've labeled all the directions and planes unit cell, so we've ticked that one off. What type of unit cells A, B, and C? How many atoms in each? We answered that at the beginning. Is the plane in A close packed? Prove quantitatively. So we know that A is FCC. So an FCC structure is close packed already. So we can have a close packed plane. If that was any other unit cell, we could have just stopped this question immediately, because if the structure is not close packed, we can't have a close packed plane. But FCC does have a close packed plane, and it actually is 1, 1, 1. But we want to prove this quantitatively. So we need to calculate our planar density, which involves basically number of atoms times area divided by the total of area of the plane. And if this magic value hits 0.9069, then we are close packed. That is the kind of the theoretical limit for the maximum packing density of equal sized basically circles. So let's see if we can calculate that out. So let's look at this plane and project it in 3 dimensions. So here we've got atoms at the corners and atoms, so like here, 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 and atoms. So you have 3 at the corner, 3 at the faces. So if we kind of project this, there's this basically, we'll see kind of this symmetry emerge. And it's the symmetry is this hexagonal symmetry. So you'll see that the corner atoms are shared by 1, 2, 3, 4, 5, 6. So each of the 3 corner atoms at the corner of our triangle is 3 divided by 6. So that's going to be just a half. So that's the contribution for the corner atoms. What about for these atoms on the side of our triangle? Well, they're just shared by 1, 2. So we have 1/2 plus 3 halves, 3 atoms times a half. That's going to give us what? How many atoms? 2. 4 halves. So we have our number of atoms is equal to 2. What's the area, or the cross-sectional area of a sphere? That's just going to be equal to pi r squared. Now, what is the area of our plane? So we have an equal size triangle, x, x, x. Hopefully you remember from geometry that the area of this triangle is going to be root 3 over 4x squared. So that's our area. What is our x? Well, we know that in FCC, these atoms are touching. So this distance is 2r, and that distance is 2r. So our x is equal to 4. So go into mathematics really quickly here. So we can look at these. So let's plug in some values. So we know that x equals 4 times r. I know that my area equals square root of 3 divided by 4. And then I want all of that times x squared. And let's go ahead and work with that. So our planar density is going to be, so PD equals 2 times pi times r squared divided by a. Let's see this out numerically. And what do you know? We hit our magic number, so we did prove quantitatively that that is a close packed plane. Excellent. Now we're moving on to Kroger-Vink notation. You will absolutely like that Kroger-Vink notation. So I'm interested in yttrium oxide, Y2O3, for its fascinating electronic properties. Write the Schottky and all Frankel defect reactions for this material. So we know that Y is going to be basically a 3 plus, right? Plus our oxygen is 2 minus. So if I'm doing a Schottky defect, I'm creating a vacancy in Y plus a vacancy in oxygen. If I create a vacancy in oxygen, I'm going from 2 minus to 0. So that's positive 2 charge. That's with the dots. If I'm going from 3 plus to 0, that is minus 3. So for charge neutrality, I need this to be 2. I need this to be 3. And that's it. Frankel defects, on the other hand, we have Y2O3. So we need to create basically a, let's look at yttrium, X. So if I put yttrium on an interstitial, that is going to be 1, 2, 3. If I put a vacancy and I kick it off and I put a vacancy in yttrium, that creates a minus 3. Do the same thing for oxygen. So oxygen interstitial, 2 minus, plus vacancy in oxygen, 2 plus. Charge neutrality, we're balanced, good to go. So that is the Frankel and Schottky defects for that material. Now, E is asking us, yttrium oxide, our host, can be doped with an impurity Ta2O5. So we know Ta2O5, actually let me erase it with here, give me some room. So we're going to write multiple reactions. So I know that Ta2O5 is going to be my impurity. That means my host Y2O3 is going to be right here. I know that Ta is 5 plus for the charge. Excellent. And I'm going to write 2 reactions. So I'm going to write this right here. So let's look at the first one. So 2 extrinsic reactions incorporating this into our yttrium oxide. One reaction must have a substitutional cation. So we're going to substitute our impurity cation, Ta, onto our yttrium. So we are going from 3 plus to 5 plus, so that is going to be a change of plus 2. And an oxygen interstitial, so I need plus oxygen interstitial, that's minus 2 charge. So now I'm charge neutral right here. So Ta, except I need 2 of these for mass balance. So I'm mass balancing across the scripts. 2 oxygens, so I need to have 3 more oxygens. Charge balance, mass balance here. Let's look at the bottom. 2 yttrium, oxygens, no oxygens here, 3 oxygens, we're good to go. So we've answered the first one right there. Now, the other reaction must have a cation and an anion interstitial and a cation vacancies. So we need a cation interstitial. So we are going to put our Ta, we're inserting that into an interstitial. So that's going to be a plus 5 charge, 4, 5. And an anion interstitial. So we need oxygen interstitial. 1, 2, that's it. And a cation vacancy. So a vacancy in the cation is going to be a vacancy in our host. So vacancy, because we could only create vacancies in the host. Vacancy in Y, so we're going from, again, 3 plus to 0, so that's going to be minus 3. So plus 5, minus 5, I'm good to go there. Let's look at charge balance. So I need to basically increase that. So I'm going to go put 2 here, and I'm going to put 2 here. I'm just going to put 2 here. So got Ta, 2 of them. Oxygens, I need to put 3 more. 3 oxygen, oxygen, X. Sorry for that, 3. So on the first side here, I'm fine. Y2 on the scripts. Yep, 2 Ys, 3 oxygens. That's it. I've got it. We're good to go. So that's all we're working with there. Now, the last part of this question asks then, we need to look at this phase diagram and then identify what the invariant points are occurring here. So this one, hopefully you've seen before. So actually, let's help. So if this is this region here is alpha plus this region here is beta plus this is liquid, this is a pure material right here, this is going to be liquid plus this, and this is going to be liquid plus this, and this is going to be liquid plus this, and this is going to be this plus this. So let's see what's happening right here first. So there we are transforming from pure liquid to beta plus Ti to nickel. Let me make sure that's right. Use my eraser. Yep, Ti2 nickel. Ti2 Ni. So that is, we know, eutectic. We can also see another eutectic point right here, right? So we are going here from liquid to a Ti-Ni plus Ti-Ni3 mixture. So this one's done, this one's done. Let's look at what's happening right here. So here we are transforming over here from liquid plus Ti-Ni going to a pure solid Ti2Ni. That is a pereutectic transformation. And then our last one right here, it looks like a eutectic, but looking at the transition, we are going from beta to an alpha plus Ti2Ni. That is a eutectoid. And again, you can look back through the notes and from exam 1 to kind of remember those. But yeah, those are all the invariant points, at least that's identified here. So you can kind of test yourself. There's another invariant point basically right here, and you can kind of work on that problem as well. So that's it. Next time, we're going to get into mechanics, and then you'll be ready for the exam. All right, let me know if you have any questions, and thanks. Bye.